welcome to the first lecture of Module 4 on heat transfer.
From this lecture onwards, I will be discussing on convection heat transfer in details, and as we have discussed previously, as already we have discussed in our introductory lectures, that convection is another method or another mechanism of heat transport from one medium to the another medium, and convection takes place by the displacement of the particles of the medium, and this happens to be due to the motion of the fluid in contact with a surface, and this motion of the fluid is possible due to two aspects. One is called density difference, and this density difference comes out or appears due to the presence of temperature difference, and as a result there will be a relative movement of the particles. Lighter particles, medium particles at higher temperature will become lighter and they will move upward, and the colder particles will be heavier and they will come down. So, there will be a circulation, and that is nothing but the convection, and this convection is called free convection or natural convection. And another mode of operation, another mechanism for this convection mode of heat transport is that comes out due to the fluid velocity. This is this is basically that the fluid is given some velocity with the help of some external agent like a pump or blower. So, pump or blower puts some mechanical energy on the fluid and the fluid starts moving, and this is the movement of the particles of the fluid which are responsible to carry the heat along with it. So, the heat transfer takes place by this movement of the fluid. It is called forced convection. So, thus these two mechanisms of convective heat transport that already we have discussed, and now also we have seen, these are, one is called free or natural convection, another is called forced convection. Okay. Now, what happens is that heat transfer for either of the mechanisms, that it is usually expressed, amount of heat transfer is usually expressed with the help of the terminology that also we have discussed, that is called heat transfer coefficient. So, heat transfer coefficient is a terminology that works as the inverse of the heat transfer resistance, and it gives an indirect understanding about the extent of heat to be transferred, or extent of heat would be transferred, or extent of heat transferred for any heat transfer processes. Now, this heat transfer coefficient usually denoted by a terminology H, and this is H is many times or H is a function of, we can view like this, fluid property. It can be function of flow property, and also it can be function of the geometry. Okay. Now, the question is that fluid property, this includes the density of the fluid, viscosity of the fluid. So, fluid property includes density, viscosity, thermal conductivity, then you have specific heat, Cp, etc. Similarly, flow property, this involves typically the velocity, heat transfer coefficient, this is a V. Heat transfer coefficient itself is also it's a flow property, it depends upon flow property is a V, and then we have geometry. So, we have to see that a characteristic length based on geometry. Okay. Now, geometry can be cylindrical, spherical, flat surface, etc. So, we can have the flow over a cylinder, over a sphere, over a flat surface. We can have a flow through a cylinder, through a inside a spherical body, okay, like that way. So, under that kind of situations, so there are different type of geometry could be possible for such heat transfer phenomena, and when you have different type of geometry, then the characteristic length depending upon the geometry has been taken to be the geometric considerations. So, heat transfer coefficients are functions of such different types of properties. Now, what happens that practical requirements for heat transfer study by the forced or free convection this forced or free convection that we come across, in those cases we usually see this happens to be in one case is convection in laminar boundary, laminar flow, or we can have convection in turbulent flow. So, that means we can have forced convection or free convection situations, and that kind of situations we can encounter either in laminar flow situation or in case of turbulent flow situation. And also we have seen that different types of geometry can be found out. For example, flow through a tube. So, flow geometry, as already we have seen, it can be flow through a tube, flow over a tube, flow over tube bundles, okay. Then like that, flow over flat plate, etc. So, as I have told already, so flow through a tube. So, when you have heat transfer between two fluids, there is a medium, and both the two fluids are moving, say in two tubes, or the one fluid is hot fluid is moving through one tube and the cold fluid is moving outside the tube. So, in both the cases it is flow through a tube or flow over a tube. Now, again the question is flow over a tube, it can be along the tube length, it can be across the tube length. Okay. So, that means flow across a tube bundle. So, flow through a tube bundle means flow across, flow over a tube bundle means flow across a tube bundle. So, this kind of situations we can come across. Similarly, flow over a flat plate. For example, a typical example of a say furnace is when you have a furnace of say a flat geometry. In that case, the flow is there flow is over a flat plate. So, that kind of situation is also there. There are many other situations when the flow takes place over a flat plate. So, that so different types of geometry as possible to discuss about the convection problems. Okay. Now, point is that the calculation of this convective heat transfer coefficient is very important to understand, as we discussed, to understand the extent of heat transfer. Now, this calculation of convective heat transfer H calculation is usually carried out by three basic ways. These are as calculation, if I say calculation ways, these are dimensional analysis, then second is solution of boundary layer equations, and analogy between use of analogy between heat and momentum transport. Okay. So, these are the ways by which we can find out the values of heat transfer coefficient, and as we told that heat transfer coefficient calculation is very important to find out the extent of heat transport. Now, there are certain difficulties in finding out the heat transfer coefficients, and if we see that all the three methods whatever we have told, that dimensional analysis or boundary layer solution of boundary layer equations or use of analogy between heat and momentum transport, in none of the cases things are complete or accurate. So, however, and all the things are having all the processes are having their inherent merits and demerits. Okay. But however, we should have some idea about all the processes, how to calculate the convective heat transfer coefficient values, and in these coming series of lectures, I will try to discuss about the different types of these heat transfer coefficient calculation procedures. Okay. Now, so to start with, what we will do is we will first study the dimensional analysis. So, if we know that mechanism of fluid motion, okay, whether it is passing through a tube or over a tube or over a spherical plate or over a flat plate, mechanism of the fluid motion is not very straightforward. It is not particularly when you have the turbulent flow situation, then mechanism of fluid motion is little complicated. Therefore, it sometimes become very difficult to find out the exact value and accurate value of heat transfer coefficients by the concepts of theories. Okay. So, therefore, sometimes it might be useful, for particularly the practical problems, it might be useful to calculate heat transfer coefficient values from empirical correlations. So, this is empirical correlation is obtained by performing a lot of experiments for in the lab scale studies, one can perform lot of experiments, and those experimental data can be correlated in the form of several dimensionless groups. Okay, and these dimensionless groups then with the dimensionless groups are used to finally find out the values of heat transfer coefficient from the experiment from correlations. So, what actually is being done? So, if suppose I have a problem, so in the lab scale I will take up this problem, I will do lot of experiments, I will generate lot of data, and those data will be then fitted into some relation. This relation is made up of some dimensionless groups, and those dimensionless groups again made up of combining several parameters related to the process, which are significant to the process, which are determining the process behavior. So, based on that we will be getting the dimensionless group, and based on the dimensionless group we will find out or generate a correlation. So, what happens, that is called the empirical correlation, and that empirical correlations happens to be valid for the kind of experiments that has been performed, for the ranges of the data that is being studied. So, there are certain ranges for which it is studied. So, it does not become an universal correlation, So, this is the deficiency, or this is the drawback of having empirical correlation, but the advantage of this is that within the span of the ranges of the span or the ranges of the different parameters, it works fine. And so, one can now if one wants to find out the values of heat transfer coefficient, he can easily find out from that analysis or from that experimental or that correlation he can use, and he can find out the values of heat transfer coefficient and then find out the value of total heat transfer. Actually, what is this total heat transfer? Once you can find out that heat transfer coefficient, that is nothing but say H, which one can find out as the average H, average heat transfer coefficient, and then that total heat transfer is, we have already seen previously that it is H A delta T. So, H is the heat transfer coefficient, that is Newton's law of cooling. H is the heat transfer coefficient, area is the A is the area of heat transfer, and delta T is the temperature difference or the driving force for the heat transfer. So, once we know these H values, we can find out the value of total amount of heat transfer. So, dimensional analysis is such a method which helps us to give or generate some empirical relationship. Now, how it helps us? One has to know that what are the dimensionless groups would be pertinent, would be important, would be significant for any particular process of heat transfer. So, through the dimensional analysis, we will finally get that kind of information, and then one doing an experiments in those kind of situations will use those dimensionless groups and try to go ahead for developing some correlations. And already we will see in future when we will go ahead with these lectures, we will see that there are such several correlations have been presented by various authors, various researchers. Some of them are extensively used, they are very important, they are very known and very famous and extensively used, and more closely or more accurately they are predicting the process performances. We will see that. Okay. So, now what we will do is through the dimensional analysis, we will try to find out the different dimensionless groups. Different dimensionless groups. What is these dimensionless groups? These groups are basically a combination of a few variables that discuss the behavior of a particular system. Suppose a system I have, I am thinking of a problem. This problem will have several variables that will to represent that problem. Now, some of the variables may club together and give a significant explanation of the process. Like that way, we can have a few such groups develop, and dimensional analysis gives us a guideline and a procedure how to generate different dimensionless groups, and we will see this with the help of some cases. Okay. So, and the procedure or the methodology we will be using is Buckingham, which is a very common methodology, is the Buckingham Buckingham pi method. Okay. So, to start with, what we will do is we will take up the case of say forced convection heat transfer. Forced convection heat transfer say through a pipe, through a circular pipe. So, we will see first we will see for forced convection heat transfer through a circular pipe, then we will see some dimensional analysis in case of free convection heat transfer problem. Now, to start with the problem, for a forced convection heat transfer through a circular pipe, and why we have taken this? Because we know that most of the industrial applications, most of the industrial processes, they do transport fluid through a pipeline, and the heat transfer takes place, heat exchange between one fluid to the other fluid always takes place when when the fluids are flowing through cylindrical geometries. Okay? That is why we have taken this problem. Now, for this case, what we have to do in case of Buckingham pi method? First, we have to understand that we have to identify the variables. So, we have to identify the variables that demonstrate that signifies the system, that defines the system properly, appropriately. I should say that define the system suitably or appropriately. So, when you would like to do that, this is one important thing. It requires definitely it requires knowledge and experience. So, these two things are very important for this identification of these. One is knowledge and second one is experience. So, I will make a table to show that what are these parameter useful for such kind of things. If you see that variables, so what are the variables? Variables should be, first one, our target is heat transfer coefficient. Say H, okay, and the unit of heat transfer coefficient is in SI unit. If we write the unit, it will be watt per meter square per degree centigrade. So, then what are the other variables? So, heat transfer coefficient is one variable that we are interested to find out these values or its expression for this. Now, what are the other things which are important? That is average fluid velocity, that is the flow property. Let us call it to be V average, and naturally this is meter per second. Okay, this unit is meter per second. Then we have pipe diameter, say that is the characteristic length, which is pipe diameter. This is a D and its unit is meter. Why we are writing the units, we will see that subsequently. Thermal conductivity, fluid property and fluid heat transfer property. Thermal conductivity K, and this is watt per meter per degree centigrade. Then we have specific heat, this is again a fluid property, Cp, this unit is watt second per kg per degree centigrade, and then we have density as rho and we know that it is kg per meter cube, and then we have viscosity mu, and it is kg per meter per second. So, if we see that we have listed down several variables, number of variables is 1, 2, 3, 4, 5, 6, 7, 7 variables, total number of variables we have listed down is 7. Let us say this is equal to say equal to say n number of variables, and we know that these variables units can be expressed in terms of fundamental dimensions. So, if I say this is dimension, so we can express these units in terms of some fundamental dimensions. So, if we say that fundamental dimensions in case of fluid mechanics, if we see that in case of fluid mechanics there are 3 fundamental dimensions. These are mass. Fluid mechanics means momentum transport, there is no energy involved. In that case, fundamental dimension is mass, then length, L, and time. Time I am writing as theta here. So, these are the very fundamental dimensions, and this is used, these fundamental dimensions are used for say momentum transport. That means in case of fluid mechanics, and in case of heat transport we add one more. So, these are m, L, theta, and temperature. Temperature is one very important fundamental dimensions. We will write it as temperature, that is T. So, this is the fundamental dimensions for heat transport. Many a times there can be one more fundamental dimensions which are used, that is in case of heat transport, that is m, L, theta, T, and energy, say Q. This is also used for heat transport. But however, what we will do is, either of the cases we can generate a similar kind of dimensionless groups, but the point is that energy is taken as a separately as a fundamental dimension, but energy also can be expressed in terms of m, L, theta, and T. That in terms of those also energy can be expressed, but somebody if he is interested he can put another fundamental dimensions like Q. So, therefore, the fundamental dimensions in heat transfer could be 4 or 5. So, in our presentation we will see, we will take the first one, that fundamental dimensions are 4, that is m, L, theta, and T. So, what we have to do, the previous table what we have done here, this table, all these units, all the variables should be expressed in terms of fundamental dimensions. So, if we do that, then we will write the heat transfer coefficient H can be written as m theta. This is one important aspect of this dimension analysis, T to the power minus 1. We should be error free in that, otherwise there will be a lot of problems. Okay. Then this is L theta to the power minus 1. Then we have, this will be L only. Then we will have m L theta to the power minus 3 and T to the power minus 1. Then we will have L square theta to the power minus 2, 2 to the power minus 1. Then we have m L minus 3 and m L to the power minus 1 theta to the power minus 1. So, this is the way we get the dimensions of the variables. These are listed for this problem of post convection heat transfer through a pipeline. Now, so what is this is if the fundamental dimensions are 4. So, if I write is that that is equal to say fundamental dimensions is equal to say m is equal to 4. If I write that, then according to Buckingham pi method, okay, according to the Buckingham pi method, the number of dimensionless groups would be P equals to say n minus m, and here it is equals to 7 minus 4 equals to 3. So, in the present situation, present problem will be getting 3 dimensionless groups that will be generated. Now, so how this will be done? If we see that, say let these dimensionless groups are say pi 1, pi 2 and pi 3. Now, comes the question of dimension analysis. So, what we will write? Pi 1 is a dimensionless group, pi 2 is a dimensionless group and pi 3 will be a dimensionless group. So, then what we will do? We have to write the pi 1, pi 2 and pi 2 expression in such a way that the variables will, some of the variables will club together and to give a dimensionless quantity. Now, to do this, we have to decide about some core variables. As because there will be 3 dimensionless groups. So, there will be 3 variables which are not core and the remaining will be the core variables. So, core variables will be then 4 and we will assume say we will take say for the present case the d, k, mu and say v are core variables. That means, these core variables, while we will do the analysis, they will appear in all the expressions of the initial, it will appear all the expressions of the dimensionless groups. We will see one by one. So, then if I write, we will write that pi 1 as say d to the power a, k to the power b, mu to the power c, and this v is v bar to the power d, and rho. Rho is another variable, I am putting rho over here. So, the power of rho is being taken care of by a, b, c, d. Okay. Similarly, we can write pi 2 is equal to d to the power e, k to the power f, mu to the power g, v bar to the power h and then c p. Okay. And then we have pi 3, say we will write d to the power I, k to the power j, mu to the power k and then v bar to the power L and then h. So, we can very clearly understand that the core variables, the meaning of the core variables will be repeating in all the dimensionless group as of now, because we do not know which is going to exist in pi 1, which is not. And then other 3 variables like rho, Cp and h, they will come only once in one of the variables and their power will be taken care of by the a, b, c, d, e, f, g, h values. Okay. So, this is very important step. Now, depending upon the choice of the core variables, we may sometimes land up with known and famous dimensionless groups, sometimes we may land up with uncommon, unfamous, unknown dimensionless groups, but we have to then regroup, rearrange those unfamous or unknown dimensionless group into the known form. Okay. that I will gradually will see that which are the very known things, which are not very known dimensionless groups. So, what we have to do now, we have to make use of the dimensional analysis. What is the dimensional analysis? If we see for pi 1, if we just do for pi 1, what will we write? For pi 1, we know that pi 1 is equal to d to the power a, k to the power b, mu to the power c, v bar to the power d and rho. Now, we know that pi 1 has to be dimensionless. So, if we write it is m to the power 0, L to the power 0, T to the power 0 and theta to the power 0. These are the 4 fundamental variables, and m to the power 0 means 1, L to the power 0 means 1, T to the power 0 means 1 and theta to the power 0 means there is no dimension actually, and this is equal to. So, d is L to the power a. I will take the dimensions already we have already shown in the table. So, we have to make use of this table in the last column of the table, we have to make use of that column. Then what we will write is L to the power a, m L theta to the power minus 3, T to the power minus 1 to the power b, then m L to the power minus 1, theta to the power minus 1, this is that for mu whole to the power c, and then L theta to the power minus 1 to the power d, this is for v bar average velocity, and then rho is m L to the power minus 3. Okay. So, this happens to be the case. Now, what we have to do? We have to see these dimensions, the powers. So, this is equal to m to the power b plus c plus 1. If you see b plus c plus 1. So, b plus c plus 1, then L to the power, we have seen a plus b, we can see m to the L to the power a, L to the power b, plus minus L to the power minus c, and then plus d minus 3. Okay. This 3 is coming here. Then theta to the power, what is there? We can see minus 3b, then minus c minus d, okay, minus c minus d, and then t to the power we have only minus b, this. So, if we see that now this is called dimension analysis. So, left hand dimensions and right hand dimensions we are matching. So, if you have to match it, then according to this b plus c plus 1 should be equal to 0. This I say equation 1. Similarly, a plus b minus c plus d minus 3 equals to 0. Let us say this is equation 2. Then we have minus 3b minus c minus d. Okay. This is equal to 0. Let us say this is equation 3, and then we have minus b equal to 0. This is equal to equation 4. So, from equation 4, we finally get that b equals to 0, correct. So, b equals to 0, then what is there? From 1, c equals to minus 1, then from 3, 1 by 1 we will calculate. In 3 we have b equals to 0, c equal to minus 1. So, we have got minus 3b minus c minus d equals to 0. This implies 0, b equal to 0, and then plus 1 minus d equal to 0. This implies that d equals to 1, and then from say the bigger one 2. So, gradually we are finding out all the values of these a, b, c, d, that powers. Okay. Then from 2, if we put all the values, we will get a equals to a plus b minus c plus d minus 3 equal to 0, or a plus b equal to 0 minus plus 1 minus 3 equal to 0. This indicates, or a equals to 1. So, then what the values we got? A equals to 1, b equals to 0, c equals to minus 1 and d equals to 1. Now, if we put these values over here, what we get? We get pi 1, then we had pi 1 as d to the power a, k to the power b, mu to the power c, v bar to the power d and rho, and we know this is a is equal to 1. So, it is d to the power 1, k b equal to 0, k to the power 0, mu to the power c is equal to minus 1, v bar to the power 1, and this is rho. So, what we can write? We can write as d v bar rho by mu. That means, it is a very known expression for us, and we know this is called Reynolds number. And we express it as Re based on diameter. So, this is d is the diameter, that is the characteristic length. So, this is Re based on diameter, and we also know what is the physical significance of the Reynolds number. We can write this as rho v bar square by mu into v bar by d. Okay? So, rho v bar square is called inertial force, and mu v bar by d is called viscous force. So, that means, what I was telling is that by this way we get an expression of a dimensionless group which is called Reynolds number. That is a very known, very popular, very famous dimensionless group that gives us or indicates us, lets us know about the flow behavior, because Reynolds number discusses about the how a fluid is flowing, whether it is flowing in turbulent flow, whether it is giving you a laminar flow. From the values of the Reynolds number, we usually do find out that, and this Reynolds number is a ratio of inertial force to viscous force. As we know that if Reynolds number is very high, means your inertial force is high relative to the viscous force. So, that means it is towards turbulence, and when Reynolds number is very low, then viscous force is dominant with respect to the inertial force. That means it is towards a laminar flow situation. That we already know in fluid mechanics and or momentum transport, we have seen it. So, one thing we can say that when there is a flow associated through a pipeline, one dimensionless group is definitely happen to be there in there, which is called Reynolds number, and it is already known who has already studied the fluid mechanics. So, exactly in the similar way, if we do the analysis, we will get pi 2 as mu Cp by k. If we do the similar analysis, this is a simple mathematics, nothing is there, exactly similar procedure. If we do, we will get pi 2 as mu Cp by k. What is this? This is again a dimensionless group, and this is written, this is called a very famous dimensionless group associated with heat transfer. It is called Prandtl number. Okay. And it is abbreviated as PR. It is a very famous dimensionless group for heat transfer. That is what I was telling. The suitable selection, proper selection of the code variables will give us known famous dimensionless groups which are already known to us. Otherwise, we may land up with some other kind of dimensionless groups, and then we may rearrange those dimensionless groups again to the known or famous dimensionless groups. Okay. Now, what is this Prandtl number? It is written as, if I do it like this, mu by rho divided by k by rho Cp. What is this? This is equal to nu by alpha. We know mu by rho is equal to nu, okay, and k by rho Cp is equal to alpha. This is called momentum diffusivity by thermal diffusivity. So, with the this Prandtl number is a ratio of two important variables is called diffusivity ratios, that is momentum diffusivity and thermal diffusivity. So, it is a dimensionless group. So, it also Prandtl number helps us to understand a relative behavior of heat transfer and fluid mechanics. this relative behavior, that will see that whether heat will be transferred earlier to momentum, or momentum will be transferred earlier to heat. These things can be discussed with respect to that values of Prandtl number. Okay. These things we will see that depending upon the Prandtl number, when we will discuss about the boundary layers, there we will see even more details, that depending upon the values of Prandtl number, we will decide whether the boundary layer of heat transfer will be above or below the boundary layer for momentum transport. That means, there are two type of boundary layers which are there. One is called thermodynamic, one is called thermal boundary layer, another is called hydrodynamic boundary layer. Hydrodynamic boundary layer is due to the flow, which discusses about the momentum transport, and thermal boundary layer which discusses about the heat transport. We will discuss that, and we will see that how the boundary layer thicknesses depends upon the two diffusivity terms which are come here as the momentum diffusivity and thermal diffusivity. So, the Prandtl number is a very important dimensionless group in that way. Okay. Then the another group, that is the pi 3 is another dimensionless group. This is pi 3. This is this will come as H L by K or H D by K. In the similar way, if we do this, we will get that pi 3 is equal to H D by K. This is also a very famous dimensionless group, and it is known as Nusselt number. It is given, it is denoted as Nu, which is very important to us, because this Nusselt number is a term, Nusselt number is the variable dimensionless group which is associated with this heat transfer coefficient value H. So, when we have to calculate the values of H, heat transfer coefficient, we have to get the value of Nusselt number. Okay. Now, Nusselt number, if we write, it can be written as like this, d by say K A divided by 1 by H A. So, I have just incorporated one area term over here. So, then it can be written like this. So, we are multiplying up and down by an area. So, we will get like this. So, this we have already seen that L by K A, this is called conductive resistance. K is the thermal conductivity, and D by K A or L by K A, which is D is the characteristic length, here it is the diameter. So, D by K is the conductive resistance, and 1 by H A is the convective resistance. So, it is becoming a ratio of two resistances. It is very interesting. So, it gives you that ratio of, so we can say that conductive resistance by convective resistance. These resistances are offered by the fluid, both the resistances are offered by the fluid. That is what we have to be very careful, because we know that K is thermal conductivity of the fluid. So, this is the conductive resistance by the fluid. We should write more clearly, it is by the fluid, and this is convective resistance by the fluid. So, that gives a more complete definition of the two. So, this is, though in short we say the conductive resistance to convective resistance. So, this is what is Nusselt number. So, Nusselt number is basically the dimensionless group that gives that heat transfer coefficient term. So, now we have seen that from the or using the dimensional analysis for the case of flow through a pipeline, we can find out that there are three dimensionless groups, and these three dimensionless groups are, we have seen, one is Reynolds number, one is Prandtl number, another is Nusselt number. So, now we know that to get the expression or relationship between them, we should have that one, we can say that if H, there should be a function say phi, where all the variables, function of all the variables equal to 0. Now, in that case, we can write that, and the other way around, say if I say another function, say f of all the dimensionless groups equals to 0. That is, so we can say that now our Nusselt number is of our importance. So, pi 3 is another function of say pi 1 and pi 2. So, this is what is the case. Nusselt number is function of, or Nusselt number we will, so many times we can write it as the diameter, based on diameter, because it is based on diameter. So, Nusselt number is a function of Reynolds, which is based on diameter, and Prandtl. So, once we have understood, that means when we have a flow through a pipeline and the heat transfer is taking place, that kind of situation, then if we have to generate any empirical relationship from the experimental data, we must be ensuring that if the empirical relationship is with the help of the dimensionless groups, then we must be ensuring that these 3 dimensionless groups must be there in the correlations. There can be some more dimensionless groups depending upon the certain other situations which we have not taken care of here. Those are these. One case is, say, I will say you that viscosity correction, that is one thing we have not taken into consideration here. Viscosity correction, one thing. Then we can have like entrance effect. So, these are the certain things which could be taken into consideration, and then we can get some more dimensionless groups, maybe octant. Okay. However, we know that there is a very famous dimensionless group that we already know, so on the flow through a pipeline, and that is given by Ditas and Boelter. Ditas and Boelter equation. What it says? It says that Nusselt based on diameter should be equal to 0.023 into Reynolds based on diameter to the power 0.8 and Prandtl to the power n. So, we can see here that this n is given as 0.4 for heating a fluid. That means Tw wall temperature is greater than fluid temperature. This is Tw is wall temperature, Tf is the fluid temperature, and n is equal to 0.3 for cooling a fluid when Tw is less than Tf. So, that means surface temperature is less than the fluid temperature. So, you are cooling the fluid. Okay? And this equation is applicable for conditions, as I told you, that this is basically the Ditas-Boelter equation is an empirical relationship, but we can see that it has taken care of all the 3 fundamental dimensionless groups, what we have already shown, that this should be fundamental dimensionless groups for discussing this flow through a pipeline and heat transfer problem. So, the conditions are turbulent flow, where that RED is greater than or equal to 10,000, then fully developed flow, that means, what does it mean? No entrance effect. Then other conditions are like smooth pipe, then we have this a range of Prandtl number 0.7 less than equal to Prandtl less than equal to 160, then D by L, this is L is the length of the tube, is less than 0.1 and moderate temperature difference between the wall, tube wall and fluid bulk. So, that means this is no viscosity correction. That means these are the conditions for which
Dietz-Boelter
equation is applicable, okay, when we have different conditions, as we have seen that it should be turbulent flow when the Reynolds number is greater than or equal to 10,000. It should be fully developed flow, that means there is no entrance effect associated with that. Then this should be a smooth pipe, that means the roughness, that means no roughness, no pipe roughness. Then Prandtl number has to be within a certain range, 0.7 less than or equal to Prandtl, less than or equal to 160, and d by L, the length to diameter to length ratio should be relatively high, therefore relatively low, that means the length should be relatively sufficiently long. So, it is d by L is less than 0.1, and moderate temperature difference between tube wall and the fluid bulk, that means there is no much viscosity corrections is involved in these. Exactly in the similar way, there are many other correlations have been given. For example, another very famous correlation is by Cedar and Tate. He says that the same case only changes is this equal to 0.027 Reynolds to the power 0.8 and Prandtl to the power 0.33 and mu by mu w to the power 0.14. So, this is the expression given by Cedar and Tate, which is very famous expression, very famous empirical relation, which is very commonly used in all heat transfer calculations. Once we know the value of Nusselt number, then we can find out the value of H heat transfer coefficient. Here the conditions remain more or less the same, and here this is the viscosity correction. Mu is the viscosity of the fluid and mu w is the viscosity of the wall. This is wall viscosity at wall temperature, viscosity of fluid at wall temperature. Mu and mu w, viscosity of fluid at bulk temperature, fluid bulk temperature and wall temperature respectively. Okay, fluid bulk temperature, and we can see that the other ranges are that Prandtl number is again 0.7 less than or equal to Prandtl, less than or equal to 16,700. It's some bigger range. Reynolds based on diameter is greater than or equal to 10,000, and d by L is less than or equal to 0.1. Okay. So, in all the cases, so this is the Cedar-Tate equation, and in both the cases, that is very important thing. We have seen that there are some physical properties which are involved in the dimensionless groups. These physical properties are rho, mu, k, Cp. Okay. So, this kind of things. So, physical properties are to be evaluated, or bulk fluid properties to be evaluated at the arithmetic mean bulk temperature, at the that means it is the average of the inlet and outlet temperature of the fluid. this is average of inlet and outlet temperature of the fluid. Okay. So, this way we can find also that using these similar kind of dimensionless groups, we can find out that expression for heat transfer coefficient Nusselt number. We can find out the value of Nusselt number. From the value of the Nusselt number, we can find out the value of heat transfer coefficient, and from the transfer coefficient values, we can calculate the value of total amount of heat transferred. So, this way we have demonstrated the problem of getting the dimensionless groups associated with a very common practical situation, that forced convection through a pipeline. Then next class will show that in case of free convection system, what are the very basic dimensionless groups that play significant role in calculating the heat transfer coefficient values, and thereafter we will show that there are lot of developments, lot of new dimensionless groups have come up, as well as a lot of new empirical relations have been used to get even better prediction or better calculation of heat transfer coefficient and better calculation of the amount of heat transfer for a particular process. We will gradually see those things in subsequent lectures. Thank you.